Hello everyone. So today in this lecture we'll be discussing about the geometry of the parabola of projectile. We know for any general conic, let it be ellipse, hyperbola or a parabola, we define a point which is called the focus, and there exists a line D which is also known as directrix, and a point which is defined as the locus. We define the locus of point P such a way that its ratio of distance from the focus and the directrix bears a real number, that is a constant, that is fp by p. Suppose this is q, pq is equals to some constant e. This is the definition of eccentricity, and for a parabola, E is equal to 1. And we know that projectile is a parabola only. So this will also have a focus and a directrix of its own. Suppose this is the directrix, and somewhere here is the focus F. Suppose that the distance between the point of projection and focus be d, and the height of the focus from the ground be h. As per the rules of parabola's eccentricity, so the distance from the directrix will also be d. Hence, this distance will be d. For now, suppose this angle to be theta. Now the theorem is that suppose any point P on the trajectory, any point P, okay, it says that if the magnitude of velocity at point P is given as u, then the distance Pf is given as u square by 2g. This is a simple formula. It may look complicated because how can we find the magnitude? We have to first square find the value of uy square plus ux square, and ux is though constant but ui is varying with time. So it may look tedious calculation, but actually no, we can use some geometrical tricks. Now suppose a parabola is at point, the point of projection is o. Now OF is D. You can also treat the parabola similarly, like we are projecting the ball from point P. Then also the parabola will be same. Just the this part will remain vacant. That is, this part will not be a part of the trajectory. But if we extend it backwards, then also we'll get the same parabola. That is why this formula is applicable for any point. Now coming to its proof, the proof is a little bit tricky geometry, nothing else. And just we have to remember that range is equals to u square sine 2 theta by g. Height of projectile is given by u square sine square theta by 2g. These two formulas are very important in this discussion. By Pythagoras theorem, I can write this distance as under root d square minus h square. Let this point be something q. So OQ can be written as under root d square minus h square. Now, an important thing to note that if we draw the axis of symmetry of a parabola, then the axis of symmetry passes through the focus. So OQ will be just half of the range, that is u square sine 2 theta by 2g, which will be u square sine theta cos theta by g. This is equation 1. Now coming back to the geometry, suppose the height of the projectile be h. This length, that is the distance at the topmost point from the directrix, will be d minus h, and distance of the topmost point from the focus will be h minus h. So d minus h is equals to capital H minus small h. From here d plus h is equals to 2h, which will come out to be u square sine square theta by g. This is equation 2. Now d square minus h square can be written as u to the power 4 sine square theta cos square theta by g square. I am just substituting the values from equation 1. Now factorizing it, d minus h into d plus h is equals to u to the power 4 sine square theta cos square theta by g square. Now dividing it by d plus h both sides. Now since we have already derived that d plus h is u square sine square theta by g, we are directly substituting it here. By g square into u square sine square theta to g. So this g cancels, here one u square sine square theta cancels, and you will get u square cos square theta by g is equal to d minus h. This is equation 3. Adding equation 2 and 3, 2 plus 3, you will get d is equals to u square sine square theta plus cos square theta by 2g, which will come out to be as u square by 2g. A very interesting result. So one must try to remember this, and let us see how to apply this in some important problems. Well, first is the proof for maximum range. Suppose this is my ground, and here is a ball which will be projected from the ground. It is projected at an angle theta with velocity u. We know the derived result that theta is equals to 45 degree, and the maximum range is given as u square sine 2 theta by g. Now how can we prove that it will be when theta is equals to 45 degree, that is u square by g? Suppose the projectile goes like this, and focus may be either inside this parabola, means above the ground and inside the parabola, or below the ground and inside the parabola, means there are two cases, either here can be the focus or here. In either case, if it subtends an angle alpha and here beta, we know that this distance is constant, d is equals to u square by 2g. So I can say that the range would be nothing but 2d cos alpha or 2d cos beta in either case. Here comes the interesting part. Now substitute d, then you will get u square by g cos alpha. If I can maximize this cos alpha, then I will get my required result. So in this case, the cos alpha should be 1. That is why alpha should be equals to 0 degrees. Means the focus will lie on the ground, not above or below. Now, one may question for how can we find alpha? Sorry. So, we know that parabolas exhibit a very interesting property of reflection. Here's a parabola. If a light comes from this point to any point, a parallel light comes along the axis of symmetry, it always passes through the focus. Now you see that my projectile is like this, and if we consider a parallel beam of light, then it should pass through the ground. That is where the focus lies. It means then this angle to be 90 degree, this to be theta, and this is also theta. So theta should be 45 degrees. Thus, the angle of projection should be at 45 degree. Hence proved. Now we'll be applying this concept in another problem. So the question is something like this. Consider a building whose dimensions are given as shown. The slanting line has length b. The two vertical lines have lengths a and c respectively. And you have to throw a projectile from the ground with some velocity u such that it crosses the building. Okay. So the question is, what should be minimum value of u such that the ball crosses the building? Well, you can also prove this result. The result is very interesting. That is root g into a plus b plus c. Just the perimeter of the roof in excluding the base and times the gravity whole square root. This is the u mean. Now how to prove it? Just the same method we used previously. Suppose we have the velocity at this point A, bu, and it reaches point B. This is the optimum solution because you can say I could have thrown it like this, but it wouldn't be no optimum. It would be a larger than the required value. That is why we are taking the case where it just passes through points A and B. For now here also we will use the same geometry concepts. 1 minute. Huh. We'll be using the same geometry concepts. If I have focus here, then it will be some d1 cos alpha plus d2 cos beta. So b should be equal to d1 plus d2, or better to say b should be less than equal to d1 plus d2. I mean to say that focus will lie on the slanting line. Here the velocity is u, then what will be the velocity at point B? It will be u square plus 2g a minus c under root. So I can say that u square by 2g, that is d1, plus u square minus u square minus 2g c minus a. Well, 1 minute. No, where it came from. U square 2g c minus a by 2g is equals to b. Now cancelling off everything, we'll get u square by g is equals to b plus c minus a, and u square is equals to g into b plus c minus a. So I haven't got the value of u min. This is the u at this point a, and this is u min required. So u min square minus 2ga is equals to g times b plus c minus a. From here we'll get u min square is equals to g into a plus b plus c. Thus u min is equals to under root g a plus b plus c. So this is how this result can be so useful in various derivations. Thank you. Have a nice day.